recorded.
So hello everybody, my name is Kayla Berry and I'm CUAHSI's Communications and Outreach Specialist. I would like to thank you for joining us today for our cyber seminar. I would also like to introduce CUAHSI's guest host for the week, or for this Friday cyber seminar, Dr. Matic from University of Arizona. He's in the Department of Hydrology and Water Resources. So thank you for joining us today. And I like to start off by asking all of our participants if you would mind typing into the chat box your affiliation. I'd like to get an idea of where you're calling in from. That would just provide a little bit of insight as to who's joining our cyber seminars, so thank you for doing that. I would also like to remind everyone that cyber seminars are recorded and they are archived on CUAHSI's cyber seminar webpage so that you're able to view those at a later date, and we have over 100 cyber seminars, so there's a wide variety to choose from. In addition, the cyber seminar series will continue next week on Friday, so if you're interested in learning about artificial DNA tracers in hydrology, please tune in then. But for today, I'd like to give the speaker over to Dr. Matic and let him introduce today's presenter, Trenton Franz.
Hello, everybody. This is Marek Zerda from the University of Arizona, and it's my pleasure to introduce Trenton Franz as today's cyber seminar speaker. Trenton has a Bachelor of Science degree in Civil Engineering from the University of Wyoming, and he got it cum laude. He also played football, college football, at the same time. But I think he decided that college football was not for him, and he went for the next easiest thing, which was the PhD in Civil and Environmental Engineering at Princeton University, which he received in 2011. In 2011, he started working at the University of Arizona as a postdoctoral researcher, and he worked on the project called COSMOS, Cosmic Ray Soil Moisture Observing System. He's still with us. He's now a research assistant professor in the Hydrology and Water Resources Department, and he continues doing cosmic ray geophysics. His research interests include ecohydrology and geophysics, and his other interests today include frisbee golf. Today he will talk about ecosystem scale measurements of water using cosmic ray neutrons. Trenton?
Thank you, Mark, and thank you for CUAHSI for inviting me here. And today I'll talk about this new cosmic ray neutron method, which is very exciting given its new scale of observations. I'd also like to thank the Cosmos project as well as project members and other site collaborators.
Okay, yeah, go ahead.
The motivation for this work is nicely summarized by a recent paper with a grand challenge issued to the global land surface community of really trying to resolve the current land surface models from 10 to 100 kilometers down to this 1 kilometer resolution. This is hopes to really improve our ability to monitor and predict the Earth's terrestrial water, energy, and biogeochemical cycles. This is really essential for understanding the future of global food production and security, as well as understanding water resources suitability, predicting flood, droughts, and the potential for climate change. So I feel these issues are nicely captured in this photograph that I took during my PhD in central Kenya. So how are we actually going to accomplish a global land surface community? First is we need really large computers. So right now the most massively parallel systems can solve up to about 1 billion unknowns. More limiting, in my opinion, is really the data needs to calibrate and validate this new generation of land surface models. So in order to run these types of models, we need really high-resolution forcing data that the atmospheric community has provided with reanalysis and other downscaling methods. In addition, we have to have an idea of how the biomass is changing in space and time, so some remote sensing products can help provide some of that information. And there's still some clear data needs in terms of the biogeochemical cycling. So the focus of this talk will actually be on measurements of soil moisture in the near surface. So I'll do three things in this talk. The first is introduce the new cosmic ray neutron probe, as well as summarize the Cosmos project. Second, I'll go over how the sensor actually works in providing area average soil moisture and give a few examples from different study sites. And finally, I'll present some of the most recent work on quantifying other pools of water or hydrogen inside the sensor support volume, as well as conducting mobile measurements of even larger scale measurements of near surface water. So when we think about ecosystem measurements, really the gold standard of measurements is from eddy covariance techniques and our understanding of energy, water, and carbon fluxes. And this is really done at this intermediate spatial scale, depending on the height of the tower and the wind speed and direction. However, what's available for the vegetation to respond in terms of the soil moisture is very difficult to get estimates at this intermediate scale. So there's this, many of these flux towers have a few profiles of point measurements, and these are not necessarily representative of the larger footprint and what's available for the vegetation. If any of you have ever tried to estimate soil moisture at this scale, it's very difficult and very time-consuming, and there's not a lot of great methods to do this. And finally, really the critical link between the energy and water balance is understanding the latent energy flux, which comes from the available sources of water in the subsurface. So just some examples of how soil moisture can vary over this intermediate scale. Here we have two different Cosmos sites where we collected point soil moisture profiles over a 200-meter radius. So this is depth versus water content, where the gray lines show the individual profiles, and the black darker line shows the average profile. So the two key points here is that, while the average profile behaves pretty smoothly, the individual point profiles are really highly variable and could be over the entire expected range of water content at these sites. So just really pounding home this point is here's the examples from 35 other Cosmos sites where this natural heterogeneity is really ubiquitous across different climates, as well as different soil moisture states, either being drying or wetting cycles. In terms of soil moisture and what we've been able to do historically, we've really been limited to a few different scales. So with the advent of the TDR sensors has really opened up new temporal scales, but at a single point. In addition, from remote sensing products, either satellite or airborne based, we're starting to be able to fill in some of these larger spatial scales, but there's clearly some gaps where a lot of the interesting hydrology and ecology can potentially still be happening. So some more recent advances in hydrogeophysics have allowed us to start to fill in some of these scales, particularly with mobile TDR and EM electromagnetic methods. But the focus of this talk will be on the cosmic ray probe, as well as the stationary, as well as the rover probe. And these are some of the new scales that we can start to fill in with this relatively new method. So the Cosmos project stands for Cosmic Ray Soil Moisture Observing System. This is an NSF-funded project that was started in 2009 and will end later this year. So the first phase of the project is the deployment of 50 of these sensors around the U.S. as a proof of concept stage. The second phase of the project, which will hopefully start next year, will be an expansion to 500 of these sensors around the U.S. So the priorities for the project were understanding the soil moisture controls on weather and climate models, as well as ecological processes and phenomena and hydrological flow processes inside of catchments. And I'll talk about in a few minutes. The sensor sees all pools of water or hydrogen, so we can look at water storage on and in vegetation canopies, as well as frozen precipitation. So the hope is that these data sets will also be very useful for some of the upcoming satellite missions, the current SMOS mission right now, and the upcoming SMAP mission to start next year. So the Cosmos data Right now we actually have 60 sensors around the continental U.S. and a few other sites around the world. The data is freely available in real time on the Cosmos website. Right now there is some quality control with some additional correction factors that come online over the next few months. We'll note that most of these sites are co-located with eddy covariance towers, so you can get some of the other ancillary data. The really exciting thing right now is that there's some other independent networks starting to pop up around the globe. This is Cosmos in Australia and Terreno in Europe. And there's about 60 other probes right now, with 100 more to come online soon. So really we are starting to see this global community with similar data sets becoming available. So moving now into how the sensor actually works, a little bit of a review of how cosmic rays work on Earth, is that physicists for a long time have known that there's this difference in the ambient amount of neutrons above the Earth's surface. So here's some experimental results from Hendrick and Edge, where they made neutron measurements away from the Earth's surface in a hot air balloon. And the key thing about this figure is that there's near the Earth's surface, there's about an 8-to-1 difference between the dry Earth ambient neutron counts and water surface. So this is the physical phenomenon that we take advantage of in these measurements. So how this works is you have a high energy particle coming in, and it hits atmospheric nuclei and creates these secondary cascades of other particles, mostly neutrons. So the figure on the left shows an example of this between two copper plates from a cloud chamber experiment in 1927. So this is what we actually recreate in terms of modeling of neutrons. So this is with a particle transport code, MCNPX. So we recreate these nucleonic cascades in the atmosphere, change the surface conditions, and understand how the probe will respond to different factors. So a summary of cosmic rays on Earth is you have these high energy particles coming in. These are mostly protons and alpha particles, and these interact with the magnetic field where their intensity is dependent on where they're coming in because of the strength of the geomagnetic field. So these high energy particles interact with atmospheric nuclei and create these secondary cascades, of which I just showed from the cloud chamber experiment. And the intensity of these cascades is dependent on the barometric pressure. So what we're really interested in is the production of fast neutrons near about 1 MeV, and then the slowing of these neutrons due to elastic collisions, which will eventually lead to thermalization and then absorption of these particles. So the key property is that these last three processes are really dependent on the chemical composition, particularly how much hydrogen is available. So why does the probe actually see hydrogen? So we're going into a little bit of how the neutrons work. Is when we look at different nucleuses, what we see for hydrogen has a relatively small nucleus. However, what a neutron sees is something very different. It sees a couple of different things. The first is its scattering cross-section, where hydrogen has a relatively large cross-section. Second is the logarithmic energy decrement per these collisions, and here hydrogen has by far the largest energy decrement during this collision process. So both of these make up the total stopping power of the elements, and we find that hydrogen has about 25 times more stopping power than the other major elements present. So this is why the sensor is really a hydrogen mass balance. However, we're not really interested in hydrogen mass per se. What we'd like to understand is actually, as hydrologists, the amount of soil moisture available. So through modeling of these nucleonic cascades, we can start to come up with some relationship between neutron counts and the mean soil moisture. And so the key thing here is that there is a nonlinear relationship between neutron counts and average volumetric soil moisture. So you may have to take into this account when you start to average heterogeneous systems. So summarizing the key neutron properties is we know from physics that there's about an 8-to-1 difference between neutron intensity above the Earth's surface between dry soil and water. For most site variations of soil moisture, we see about a 3-to-1 difference. Second is hydrogen has a stopping power that's about 25 times greater than the other major elements present. And third, in terms of mixing of the neutrons, is from the nuclear cross-sections. We know that neutrons have an average jump length of about 30 meters in air, and during this scattering process, they go through about 20 to 60 of these collisions when they start out at about 1 MeV down to 10 eV. In addition, these neutrons are traveling with very high velocities greater than 10 kilometers per second. So this leads to our key assumption about why the sensor works, is we have this well-mixed neutron density in the air, where nature performs averaging of this complex system, and we can essentially sample the average property of this system at a single point with the detector. So this is what one of the actual detectors looks like. So this consists of two proportional counters. So these are the helium-3 detectors. One is unshielded, so this measures the lower energy neutrons. And the other detector underneath this layer of plastic, which shields out some of the lower energy values, is the fast neutron detector. And so how this works is you have a neutron that comes in, hits this helium-3 gas, the gas becomes ionized, and it kicks off an electron that accumulates on this high voltage wire that runs through these gas canisters. Using a high voltage source, we're able to shape that those distributions of electrons and use a data recorder to count the individual neutrons passing through these gas chambers. So this is what the entire the sensor looks like. It consists of these two proportional counters, a high voltage source, a data logger, a car battery, and then a solar panel and charging system. In addition, from each of the probes, we also have an Iridium satellite modem, which sends an email every hour to us here at the University of Arizona, and then we update the survey and update the network every hour. So this is a picture of Darren Desilets, one of the inventors of the probe, and he actually sells them commercially with his company, Hydronova. So as I mentioned before, there is a nonlinear relationship between neutron counts and soil moisture. And so some of the early work that Darren did was actually coming up with a calibration function between these two. And the key thing is that you need one known estimate of water content and neutron count rate to parameterize this relationship, this N0 value. So this is actually where I came in and why I was hired for this project originally, was to help install these sensors as well as calibrate them. And this requires lots and lots of soil samples to come up with a good estimate of the mean at these intermediate spatial scales. So how we calibrate the sensor is in this particular pattern where we sample at 18 locations in 6 depths. And so we choose we sample every 60 degrees in radii of 25, 75, and 200 meters. This is such that each of these red areas defined by the X's have equal horizontal weight to the sensor. So areas closer to the sensor are more sensitive. So the key metric that we like to have is a spatial standard error of the mean that's less than about 0.5% by volume for this calibration of N0. In terms of the uncertainty of the measurements, it's a very simple process. So the counting rate follows Poissonian counting statistics. So that means that the mean count rate is also equal to the variance. So we define the uncertainty as the standard deviation of this count rate. And so you have this trade-off between integration time and reducing the amount of uncertainty you have in terms of the Poissonian counting statistics versus how fast your system is changing in terms of the water inside of it. So what we like for the Cosmos project is to have about a 3% uncertainty on the measurements, or at least 1,000 count rate per hour. In terms of the support volume of the instrument, we define this as where 86% of the neutrons are coming from, so the 86% cumulative sensitivity line. And at sea level, this is at about a 335 meter radius circle. So the nice thing about the sensor is that the horizontal extent is not a function of the system being dry or wet. I will note that the support area does increase with altitude by the ratio of air density. So you actually get much larger aerial extents at higher elevations. More complicating, though, is the depth of the sensor does change with water content. So in wet soils, we only see about 12 centimeters, but in dry conditions, we see about 70 centimeters. So you do have this moving vertical support, which is something you will need to take into account. So in addition to digging lots of holes and calibrating these sensors, I looked at this particular problem of how different wetting and drying cycles actually affect our estimate of effective depth, as well as the uncertainty in those relationships. So in this paper, which I'll just summarize here, is we're able to derive a simple framework for calculating the sensor depth, as well as look at the uncertainty in wetting and drying cycles. And so what we find with coarse textured soils that have these very sharp wetting fronts is you may see some hysteresis in this relationship between neutron counts and average water content. But at these intermediate spatial scales, this is very unlikely to have these very sharp wetting fronts over the entire domain. So moving into a site example, so this is one of our Cosmos sites in southern Arizona, the Santa Rita Experimental Range. So this site's about 35 kilometers south of Tucson, and we receive 400 millimeters of rainfall, where about half of it is in this summer monsoon between July and September. So the figure on the right shows the location of the Cosmos sensor by the black X, as well as what the sensor is seeing in terms of the vegetation and topography within its measurement area. So the point of this study was to actually validate the mean soil moisture response that we're getting from Cosmos versus the distributed sensor network. So at each of these 18 locations, we installed TDT sensors in June of 2011. Now, each of these 18 sites, we actually put in profiles beneath the canopy as well as in the open area to come up with a good estimate of this representative area. Initially, we put in sensors at 10, 20, 30, and 50, 70 centimeters. Later went back and added a 5-centimeter probe, which I'll talk a little bit more about. In addition, at the site, we also had an eddy covariance tower that we could look at some of the surface energy fluxes. So this is the type of data that you get from the Cosmos probe. So this is our estimate of soil moisture, hourly estimate. So the uncertainty that you see in the soil moisture is due to the neutron counting statistics. And using the simple framework in the WR paper, we could estimate the effective depth of the sensor and how that changed with time and water content. And the lower panel just shows the daily rainfalls. So we have some validation that when it rains, you do see some response in the neutron sensor, which is nice to see. So with our ability to now average these point sensors, we can come up with something that would be consistent with what the Cosmos sensor would see in terms of its horizontal and vertical sensitivity. So the blue line here shows the cosmic ray soil moisture values, and then the TDT average data. So what we find over the year, or over the 6-month period, is that the root mean squared error is very small, about 1%. So we are having pretty consistent values between the sensors. I will note that during peak wetting conditions, we do have about maximum differences on the order of 3 to 4%. And we think what's happening here is because we're not capturing this top 5-centimeter soil moisture dynamics with the TDT sensors. So this is why we went back and added the 5-centimeter sensor to help resolve some of this uncertainty. But overall, we're very confident in the average soil moisture response. Well, soil moisture is interesting. Really what you want to look at is if you can compute reasonable estimates of water flux. So from the site, we also did a simple experiment of just a simple control volume where we have rainfall coming in and being partitioned to runoff and effective infiltration during a rain event. And in between rain events, you have ET, or evapotranspiration, and leakage moving out of this control volume. So the equation on the right just show these simple calculations of looking at the change in water content with time to compute effective infiltration during rain events. And in between rain events, you have net flux of evapotranspiration plus leakage happening out of the control volume. So at the site, we can use the eddy covariance tower to estimate total ET of the system. So that's shown in the top graph for this site in between 2011 and 2012. And the middle panel shows our estimates of ET from the cosmic ray neutron probe. What we find is that the data is more noisy for the cosmic ray neutron probe. However, the magnitude of the events as well as the timing are pretty consistent. So there is some initial hope that we can get reasonable estimates of flux by using cosmic ray data. So moving now into some of the other pools of hydrogen in the footprint, is we can this idea that other hydrogen is affecting neutron measurement is not new. So some of the early work with the classic soil neutron probe really identified that soil hydrocarbons may potentially affect some of these measurements. And so they did some work, some of the agronomists, on quantifying some of these other pools of hydrous and the humus, as well as attached with the organic carbon. And basically what they argued is that most of these sites are in agricultural fields, so there's a high amount of water, so we don't really have to worry about this background hydrogen. And given the small support volume on the order of 30 centimeters, we can just do local calibration for these sensors. So what's different about our sensor is that we have several sources of hydrogen. So the figure didn't show up here, but anyways, so we have a much larger support volume that we have to consider, and we've identified transient, quasi-static, and static sources of hydrogen that may be changing inside the measurement volume. And so what we're really start out being interested in is soil moisture. However, water vapor and intercepted water may also be highly transient, and something we'll have to take out of the data to provide better estimates of soil moisture. So some recent work was actually coming up with a general framework to remove some of these other hydrogen signals from the data, or potentially isolate some of these signals. So the framework first is quantifying the support volume of the measurement. Next is identifying all the sources of hydrogen in the support volume, and then trying to quantify some of these other fluxes of hydrogen into and out of the support volume. As I mentioned before, the real complicating thing is that the support volume is a function of the amount and potentially the distribution of hydrogen in the system. So this is a complicating factor that you need to consider in this framework. One area that we looked with the Cosmos project is actually looking at spatial maps of lattice water now. So this is the amount of hydrogen that's contained in the actual mineral structure of the soils. So fortunately, this is a pretty complex process. So this is both a function of soil formation as well as physical and chemical weathering. Typically, we see a higher lattice water with higher clay contents, but this is something that you will have to sample locally, which is very easy to do with a few grams of soil. This is just a map of different Cosmos sites and some of the background hydrogen at those sites. The second area that we looked at was in terms of water vapor and how that can be changing inside this the top 335 meters of the atmosphere, or near the ground surface, excuse me. So this is just a simple relationship between relative humidity, temperature, and then how much integrated water vapor is in this top 335 meters in terms of liquid water on the scale there. So you can use this estimate of integrated water vapor and then compare the contribution of total water vapor in terms of its hydrogen component to the total amount of hydrogen within the measurement volume. So this shows integrated water vapor versus different volumetric water contents. What we find is that the contribution to the signal can range from 0 to maybe 15 or 20% of the entire neutron signal. So some very recent work is actually trying to pull out some of the estimates of biomass from these measurements. So this is a similar or the same diagram as the water vapor, but now in terms of above ground biomass versus water content and its potential contribution to the total neutron signal. So using this general framework, we can start to look at how biomass would change versus expected neutron counts for different amounts of soil water. So this is just a figure illustrating different soil water contents versus biomass water equivalents and the kind of count rates, kind of differences that we would expect for different above ground biomass signals. So that was the motivation for some work that we started in Flagstaff, Arizona last year, where we had two of these cosmic ray sensors co-located. So one was in a intact ponderosa pine forest, and the other was 3 kilometers away in this recently burned area. So with in situ sampling, we were able to show that really how these two sites mostly differed was by the above ground biomass. And what we find from the neutron data during soil drying as well as wetting is you have this consistent difference between the wildfire and pine forest site of about 100 counts per hour. So using this general framework, you can use that difference in neutron counts to come up with a biomass water equivalent estimate of about 28 millimeters of above ground material. And this compared nicely with site allometric relationships of biomass between 22 and 32 millimeters. In addition to the forest, we also did this similar study in biomass in a maize field in Iowa. So this was some work with Brian Hornbuckle and Samantha Irvin, where in addition to collecting soil samples at different time periods, they also quantified the total biomass, how much wet material, how much water there was, and also the dry mass. And corn is very interesting because the amount of water inside of it rapidly changes during different reproductive stages. So this was something that we were actually able to capture with the Cosmos sensor. Is again, this is a biomass derived neutron equivalent shown by the blue line here, and the green and yellow area show the above ground biomass. So what was interesting is that the signals do compare pretty well, but early on in June and July, we saw this big difference in terms of the neutron-derived values. What we think is happening is that it's actually picking up on some of the below-ground biomass that we didn't capture with the above-ground measurements. This was really confirmed by the last measurements in March and May, where soil tillage occurred between these two different calibration time periods, and we see this sharp decrease in the biomass water equivalent, and this is because we're removing some of the crop residue as well as exposing it to the atmosphere, so some of the roots can start to dry out. And why this is really interesting is we can now start to provide some more constraint in terms of the carbon balance of some of these systems is from cosmic ray neutrons, as we see both the fixed biological hydrogen as well as the biological water. So we want to really start to understand the carbon balance of forests, whether they're sources or sinks. This may be a very useful tool to help constrain some of those estimates. And the final part that I'd like to talk about is just some of the recent measurements that we've made with the Cosmos rover. So this is essentially just a larger version of the stationary probe with a lot more helium-3 gas. So here we see the design of the sensor in the top left versus what it actually is built and what we're using right now in Tucson. So, oops, that figure didn't show up either. Anyway, so this is some data from Tucson. I'm working with a master's student, Bobby Chrisman, and he was able to take monthly surveys of the entire basin in the dry season, and also weekly surveys of the Tucson basin during the wet season. So in the figure that you're supposed to see is the Tucson basin, which is about 25 by 40 kilometers, and this includes both the urban environment as well as the natural desert, and then some irrigation agriculture. So we have with the Cosmos rover, we're able to take data about every 1 minute to come up with stable neutron counts, and so that's just some of the raw data that is in the middle panel. Let's see. Okay, good. So these are the type of data sets that they can actually get from the rover. So again, this is a 25 by 40 kilometer area. On the top left corner, you see the Tucson urban area, which is relatively wet in January through June compared to the surrounding desert. Started the monsoons is in July, and we see the wet up of the entire basin, and then it's starting to dry out in terms of water content in September. And so the interesting things about the Tucson Basin is you have this oasis effect where the urban environment, because of irrigation, is always wetter than the surrounding desert areas. So the next steps are to use some of these types of data sets in mesoscale modeling and see if there's any impact of this urban oasis effect on the actual convective nature of storms. So the last part of Bobby's work is actually trying to confirm these measurements. So he's using some simple models to construct a basin scale water balance where he's looking at the closure of estimating total precipitation in the basin versus what we see with the sensor in terms of evapotranspiration and total leakage from the system. So he's starting to get a pretty decent mass balance closure, so we have some confidence that these measurements are providing accurate basin scale water mass balances. So just summarizing, I hope I've shown that the cosmic ray probe is a nice new technology of filling this gap between point measurements and remote sensing of soil moisture. Really the exciting thing that's really starting to happen over the last year are these other networks popping up. So we hopefully will provide these nice global standardized data sets for different communities. So as I mentioned, the probe sees all hydrogen pools within its support volume. Well, this is a slight complication for estimating soil moisture and its accuracy. This is a really exciting advance in terms of the terrestrial hydrometeorology or potentially ecology with the estimates of biomass. And finally, as I just summarized, a simple framework for trying to isolate any of these hydrogen pools from the signal. It's really the next steps are looking at can we better quantify above and below ground biomass and potentially soil organic carbons and other interesting pools of hydrogen. So this is really where we need your help, as we have this abundance of cosmic ray probe data available at many study sites across the U.S. and globe, and really need additional field studies to help quantify and separate out some of these pools that the sensor is seeing. So some areas that are really open right now are can we look at canopy interception and start to quantify its temporal dynamics. Third is again trying to partition above and below ground biomass and potentially some of the crop residue and other soil hydrocarbons. And finally, as I just mentioned, that we do measure two different energy levels, a thermal and fast neutron energy level. And so these two measurements are pretty independent of each other. So the hope is to now try and start to use them and see if we can solve for two unknown hydrogen pools at the same time with these types of instruments. With that, I'll just give my references, and I'm happy to take any questions. I think we have some time for that. All right. So I guess if anyone wants to type in the chat box, I'll try and answer your questions.
So what happens now? Are we closing the seminar or?
Oh, sorry, Trenton?
Yes, I'm all done. So I'll take any questions.
Oh, no, sorry, I was on mute. I just wanted to say thank you for your talk today. I appreciate that. If we have any questions, feel free to speak up. If you're on the line, you could unmute your phone or type them into the chat box if you have any for Trenton.
All right, so we have one question. Is there a direction in which the measurements are made? So this is the neutrons come from all directions, so it's this well-mixing process. So the sensor sees all neutrons from this area where it's more sensitive to areas right beneath the sensor. So there's no easy way to do directional measurements, unfortunately. But you can, we are trying to think of ways to use tomography like other geophysics to help maybe get more highly, better resolved measurements in space. Are you aware of the vegetation optical deaths that derive from passive microwave remote sensing? Yeah, I'm a little familiar with that, but this is something I'd definitely like to look at other cosmos sites and see if we can help identify the amount of vegetation, the water column vegetation, and potentially use cosmos to help inform some of the passive microwave measurements to really help with those algorithms and take that part of the signal out of passive microwave. Yeah, it's very coarse. So hopefully the rover and potentially some other measurement techniques of mapping larger areas with the rover, potentially some new work we've been trying to do is actually drive around a tower with a sensor and use 2 cosmos per measurement above and below the surface to try and pull out the biomass signal and do large-scale maps of that.
All right. Were there any other questions for Trenton? Trenton, is there anything else you'd like to add?
I'd just like to say thank you, and please let me know if you have any questions or need access to the data. Thank you.
Yes, absolutely. So if any questions come up later, feel free to email me, kberry@quasi.org, and I can always get you in touch with Trenton. I'd just like to remind you again, this is being recorded and will be posted next week to Quasi's website. Otherwise, thank you, Trenton, again for a wonderful presentation today. Thank you to Medic for being our host for the series today, and we look forward to having you all on the line next week.
And thank you, Kyla.
You're welcome. Have a great weekend, everybody.
You too. Thank you, Trenton. A good job.
Thanks.
Bye.
All right, thank you, everybody. Goodbye.